Good afternoon, and thank you for coming. I want to tell you in this brief presentation a little bit about some of the new research in nanotechnology in my lab. And you may have heard a lot about nanotechnology, so I want to spend a little bit of time explaining what it is, because it might not immediately be clear to you what those terms exactly mean, even though you read about it in a newspaper nowadays all the time. First of all, that picture there, that big black bar you see is a microscope picture of a human hair, and the little fiber that you see wrapped around giving light is a nanofiber, a fiber that is on the nanoscale. So right away you can see that nano scale means something that's much smaller than a human hair. So this talk, as that picture shows, because the picture gives you the essence of my entire talk, bending light at a scale much smaller than a human hair. Normally, if I take a laser beam or any light beam and I shine it up, it goes in a straight line. It doesn't bend, it goes straight. You need to do something in order to bend the light. You could use a mirror, but that's not very convenient if you have to send the light far away, which you need to do nowadays whenever you place, for example, a telephone call or you make an internet connection. The signal that goes from your computer to whichever computer you connect to, or from your telephone to whichever telephone you connect to, travels in the form of light through an optical fiber. And that fiber bends the light in whatever shape the path needs to take to go from one device to another. So that's one of the things I want to tell you a little bit about. I want to tell you about guiding light, and I want to tell you a little bit about nanotechnology. Nanotechnology means the fabrication of devices on the nanometer scale. A meter is about a little bit more than 3 feet, this size. And nano means 1 billionth. So 1 meter, big step. Let's divide it by 1,000. You get to a millimeter, which is the spacing between my fingers right now, very little here, which is about the size of a pinhead. Divide that by another factor of 1,000, and you get to what is called a micrometer, which is the size of a human red blood cell. A human hair, the one I showed in the beginning, has a diameter of about 100 micrometers. So you could put 100 red blood cells next to each other in order to get the thickness of a human hair. A nanometer is 1,000th of that. It's the size of a virus. It's about 100,000th the diameter of a hair. Why are we interested in that? Because we'd like to build devices that are very small for many reasons. I'll come back to that at the end of this short presentation. So that's why nanotechnology is important. It's at the frontier of science and technology, trying to make little devices the size of 1 nanometer. Okay, so now let's talk about guiding light, the other ingredient of my talk. Guiding light means transporting it from one point in space to another point in space. And not necessarily along a straight line, because that would be trivial. You just shine a flashlight or a laser beam or anything else from one point to the other. No, we want to get it from inside your house, somewhere in the Boston area, to, let's say, some other house in San Francisco, traveling through the ground, maybe little bits of pieces through the air, but most of it through the ground through optical fibers. How do we do that? Well, you might think that's odd that we can actually use materials to bend the light, but it's something you may have seen. If you swim underwater and you look up at the surface, something we don't usually do because it's sort of awkward to go underwater and raise your head. The air goes out of your nose and water comes in, so it's unpleasant. But if you actually look up at the surface of the water, what do you see? How many of you have ever been swimming underwater and looked up? What do you see? A mirror, exactly. If you look up, it looks as if the surface of the water is metallic. It looks like a mirror, like there's some silver coating on the water. As you can see in this picture, you can actually see the reflection of the girl's bathing suit in the surface. And the more quiet the surface of the water is, the more still it is, the better you see that it actually acts like a mirror. So here's another picture of a woman sitting on the ground, and you can see the reflections of her fins in the surface of the water. Now, incidentally, that's when you go from inside the water looking up towards the outside. Let me show you a few pictures I took actually in my kitchen table a few days ago. Here's a wine glass filled not with wine but water, and as you can see, it looks like a mirror. It's reflecting a white surface on which I put this wine glass. And if I put a marker on top of the wine glass, you cannot see the marker. You cannot see at all towards the outside. In fact, if I hold another marker below the wine glass, you can see the reflection of that marker on that surface of the water. If you look at this woman sitting on the ground there below the water from the top, you can actually see her legs. So you can look into the water, but not out of the water. The interface between water or plastic or any other transparent material, glass, acts like a perfect one-way mirror. So why is that? The reason is that light, which travels very fast, but not infinitely fast, travels more slowly inside a dense material like plastic or water than inside air. So as this light beam here, for example, travels first through the air, and then if it hits glass such as this, it slows down a bit. It slows down by about 30% as it gets inside this glass. Still very fast, covering 1 foot in about 1/1000th of a second, but a hair more slowly. So why is that important? Well, imagine a light ray incident perpendicularly to some transparent material, say water. Inside it's going to travel more slowly, so these crests of the light wave are spaced more closely. Now imagine it comes in not straight, but it comes in at an angle. Right? If it comes in at an angle, one side is going to hit the water before the other side. So now imagine an axle that is traveling on a hard surface and then reaches the boundary between that hard surface and sand, and one wheel hits the sand before the other wheel hits the sand. What will happen? It will rotate, exactly. It will rotate, it will bend. And the same thing happens with water. If you take a ray of light and you shine it into water, the angle will change. Now, suppose I make the angle larger than it is right now. Here we have a certain angle. I make the angle bigger. What will happen to the amount of bending that occurs? It will become more pronounced, right? Because this one side hits the slower medium, the sand, more early than the other side. So the bigger the angle, the more pronounced the bending is. This a little bit, this more strongly, and so forth. That is true when you go from air to water. But what if you go from the water to the air, the other way around? So suppose that we took that light beam and we inverted it. Instead of going from the air to the water, we go from the water to the air, but we use exactly the same angle. So let's look at this diagram. So if it goes straight, it comes straight out. Little angle, a little bit of bending, bigger angle, more bending. And you can already see that something funny is going to happen. But if I make this angle a little bit bigger, I reach what is called a critical angle, where the ray is going to travel right along the surface. And of course, there's one more ray, which I'm not showing here. There's a reflected ray, because there's also going to be a little bit of reflection of this surface. So as you have this ray, there's a reflected ray, and there's a bent ray called a refracted ray. And here, the refracted ray is parallel. So what is going to happen if I make the angle larger than this? All of the light will be reflected. It will be like an absolutely perfect mirror. If you look in the mirror in the morning, you wake up and wash your face, you look in the mirror, that is a pretty good mirror. That's why we use it as mirrors. It's a silver surface, but the reflection is not perfect. About 1% or a fraction of a percent of the light gets lost at the interface in the metal that is coated onto the glass and the glass itself. This mirror, however, is absolutely perfect. It reflects 100% exactly to an infinite accuracy of the light. It's called a phenomenon called a total internal reflection. Okay, so let's imagine putting our head below the water, as that circle indicates, and what you'll see is that within a certain cone angle, the light rays will go outside of the water, and conversely, the light from outside the water will go inside the water within that given cone angle. But outside that cone angle, everything is going to be completely reflected. So that means that to the left and to the right of that critical angle, the water looks like a mirror. So thinking about that for a moment, suppose you're lying on your back on the bottom of a swimming pool and the water is completely still. what would the surface of that pool look like? So you lie on your back and you look straight up. What do you see? A what?
A mirror.
A mirror, yes, but only a mirror on the left and the right in this diagram. In the center, you should be able to see out. What will be the shape of that area through which you can see the outside world? You'd see a circle. Now, very few of us have seen that because it's really hard to lie on the back on the bottom of a pool and wait long enough for the surface to be completely still. But I have some pictures to actually show to you that circle. Here's a girl holding a fish, and you can see the edge of that circle. And notice how you see the trees at the edge of the water, right? Those are the rays that come at the edge of that mirror and go straight to the edge. And here's a picture in the sea, in the ocean, looking up, and you can actually see that circle. So outside the circle, it's a mirror, but because the sea is deep, it's dark, so you can't actually see the bottom. Here's another picture that shows the edge of a pool, and notice that even though you only see within a limited circle, you can see the entire world around. The edge of the pool, the tiles at the edge of the pool are actually visible right there. You can see them. So you can see the entire world around. It's not that this mirror prevents you from seeing something outside.